experimental microstructures that you get from looking at a cross-section of metal and etching it to bring out contrast so you see the boundaries better. And if we wanted to describe this as a mathematical object, I think what I would probably do is I would probably take this regular cell complex and I would extend it to all of the plane, all of R2. And then what you do is, by an appropriate rescaling, you can go from something like this to something like this. These are actually two microstructures drawn from steel. The same length scale. These are both 100 micron bars, just to give you some kind of reference. And you see that up to a rescaling, these look very, very similar.
How were they treated? Was the first one
they're treated
cooled slower or something?
Well, probably what was going on is this one was just annealed. So all of these, I mean, all the boundaries have some excess energy associated with them, and if you bring it up to about, if you bring a metal up to about 2/3 of its melting temperature, right, the kinetics are fast enough that this happens on reasonable time scales, like a couple hours. And so you could go from this to this, you know, just in, I mean, in the time you could wait, you could sit at the laboratory bench and wait for that to happen. If it was steel, you would probably have to be at, I mean, depending on the alloy, 600 degrees Celsius or so.
That's what the word anneal means?
Yeah, anneal just means to raise it to some elevated temperature and to allow it to stay there.
I've heard it, well, used all the time.
Yeah, it's actually, there's a great deal of science involved in it. It's not just as simple as, so the rate of the kinetics by which this process happens depends exponentially on the, well, it's a Boltzmann relation, where this is the temperature. This is the rate, this is proportional to the rate at which this process happens. Arrhenius law, thank you. That's right. It goes as an Arrhenius law. And so this happens all the time. It happens at room temperature also. It's just the kinetics are so slow you never observe it for steels. But if you raise it up to those elevated temperatures, at certain temperatures actually new phases, new structures will become thermodynamically stable. And so you can have decompositions, you can have very complicated chemical reactions. So it's a very complicated procedure.
Do you generally anneal something after it's been formed into its final shape?
Well,
afterwards?
So in industrial processes, it's actually, annealing is a very costly procedure. Because, first of all, the energy that you have to put into one of these furnaces is just enormous. And secondly, in industry, you don't want to have stuff just sitting around, right? This is why aged cognac is so expensive. You just put it in a warehouse somewhere and leave it there for, 10 years, 20 years. You have to pay for that all that time, which is just sitting in a warehouse. So in industry, for example, if you're making steel pipes, what happens is you've got a block of steel and you essentially force a kind of, it's shaped like a bullet, but you force it down the center of this rod of semi-molten metal and just force it around the outsides, and then you can form it kind of dynamically. And as you're forming it, this thing is at 800 degrees Celsius. It's just on the point of being a liquid. And so it's going through the system at like 10 meters a second or more. So it's really a tremendous operation. And they're doing all of this mechanical forming to it during that process. And so you have this very complicated dynamic equilibrium going on where you introduce mechanical energy by this deformation, and then it gets annealed out at the same time. It's really fascinating and very complicated, and not what we're going to be looking at today. We're going to be looking at something simpler. So this is a section from a three-dimensional cell complex. We kind of idealize it by looking at something like this. Again, it's kind of the idealized mathematical object. This would be just cover the plane. It's not necessarily periodic. That's difficult to do. We do numerical simulations of these things, and so to get around that, we put it on the torus. And so specifically, what we do in the case of grain growth, in the case of these experimental microstructures that are drawn from metal, we kind of discretize the network in this way. It's a fairly simple data structure. We have one kind of node associated with these boundaries, with these vertices. We have another kind of node associated with breaking up the boundaries so that we can accommodate curvature of these things. These are all actually straight line segments. So it's a regular cell complex. We have two cells meeting at an edge. I'm also occasionally going to call this a boundary. We have three of these edges meeting at a vertex, which is sometimes also referred to as a triple point. There's a boundary energy associated with each one of these things. And so the system naturally wants to eliminate that boundary length. That's the driving force for this process that's governed by this Arrhenius law. The Arrhenius law tells you the rate at which it can eliminate that excess energy associated with the boundary. And so it does this by a mean curvature flow, which has this kind of interesting property that if this was a continuous system, if this was a physical system, what you would do is you would only need, you could tell where the point associated with this boundary right there will move in the next time step using only information about the structure contained in a ball of arbitrarily small radius. It's an inherently local process because from that ball I can determine the curvature of the boundary locally, and the point is just going to move in a direction of the center of curvature at a rate proportional to the curvature. And so it almost completely disregards the rest of the network. It's a very localized thing. Bob, you're furrowing your brow. Did I say something wrong?
No.
Okay.
So Jeremy, is it easy, or is it possible to write down a formula for that energy?
For the boundary energy?
Yeah.
Yes. In true systems, it's an extraordinarily complicated quantity. It resides in, depending on who you talk to, a 5-dimensional or a 7-dimensional space. And the 7 dimensions are not equal.
The energy itself is just one.
It's a scalar.
It's a scalar.
Yeah. But it's a function, for example, so in 3 dimensions, this is going to be some crystal. It has some orientation associated with it. So that's several degrees of freedom. You have a number of degrees of freedom for the orientation of the cell on the other side. You have a couple degrees of freedom associated with the boundary plane in 3 dimensions. And then you can have microscopic realignments to cause the crystal lattice to line up on either side. So it ends up being a very complicated thing. We have some kind of empirical rules for it, nothing specific. This is actually one of the great shortcomings of my field. But we assume that it's just constant. For our system, we take it as constant.
You take the boundary energy as constant?
Yeah. Yeah.
Okay.
It's
Even
proportional
after
to the air, to the length in 2 dimensions or the area in 2 dimensions.
Yeah, I'm sorry. This is a boundary energy density. This is equivalent to a line tension.
Okay. So it's mean curvature flow, then basically you're flowing along the gradient?
Yes,
Yes.
that's exactly right.
Okay.
That's exactly right. And so the consequences of this, you can think about this. It's actually the units of a boundary energy per unit length are identical to the units of a line tension. And these are numerically equivalent also. And so what you can just think about, you just think that, well, what it's doing is it's just pulling, right? It's essentially a rubber band, and it's trying to relax. And so what's going to happen is this red vertex is going to move to the location that minimizes the length of these 3 boundaries that connect to the 3 neighboring blue points. So it does that by having the angles around the vertices converge to 2 pi over 3. That's a very natural consequence. And this is the von Neumann-Mullins relation. This is kind of a result of this mean curvature flow. It's actually not that difficult to show that the rate of change of the area of a cell in time is just proportional to the number of sides minus 6. And so you see right away that there's this interrelationship between the geometry and the topology in this system. It's very difficult to separate one from the other completely. They're kind of intertwined through the dynamics in this way. Yep. Sorry? Mm-hmm.
So this is global DADT?
This is the rate of change of the area of a particular grain. So the rate of change of area of this grain in time is going to be some numerical factors times 1, minus 1 actually, because the number of sides of this grain is 5. So it's going to be shrinking in time. It's going to be shrinking half as fast as a 4-sided grain would.
What's M represent in that equation?
M, this is the mobility.
But it's whatever that means, that's a constant?
Yeah, technically the mobility is proportional to this term with some stuff out in front, so you're assuming that this is happening at constant temperature. But yeah, we essentially just take it as some numerical value and then forget about it. Okay. And so there's three topological events that happen. I'll show you a video of this in a second, and it's this very smooth procedure, except when these, except at certain points. It's the smooth flow that's punctuated by certain events. One of which is the disappearance of a diagon. So whenever one of these events happens, the topology of the system changes. In this case, you just have an edge and then a two-sided cell, which vanishes when the area of the cell goes to 0. That's this kind of singular event. It was believed, and it is currently believed, that you also have this kind of event, that you have three edges coming together with a three-sided cell which vanishes continuously to a point. This is actually open. This was believed for a long time to be one of the elementary topological events. We're now not sure of that, but that's very new.
So no one's observed it?
No, well, so the difficulty with this is it could be that you can think about some kind of configuration space, and you can talk about, just in this case, you can talk about the locations of these points where these edges come into the circle. And so there's going to be at least one point where these are exactly 120 degrees apart, that this is going to vanish continuously to a point. But that may be the only one. It may be a closed set. So if you move infinitesimally away from that configuration, it's possible that one of these edges is going to vanish and it's going to go to a two-gon before it dies. It's not clear, which would be an amazing result if that could be proven. And the other event is, so instead of a cell area going to 0, we have a boundary length going to 0. And that actually occurs just by flipping an edge. You'll notice, interestingly, that the points, so these angles are all 120 degrees. The points of where these edges meet the circle are the same in both these cases. So there's some hysteresis associated with this process. So here is a video of one of these things happening.
So that's the Voronoi to begin with?
Yep, that was a Voronoi tessellation containing points that were randomly distributed on the torus. It's just a unit square with the opposite edges identified that started with about 2,000 cells. And it's this very smooth process right up until one of the areas goes to 0 or one of the edge lengths goes to 0, and then it's punctuated by this topological event, which is making this problem very difficult to attack on the side of theory. It's not just a smooth flow. This smooth flow, which is kind of governed by the topology, connects to changes in the geometry, which then affect subsequent changes in topology. It kind of flows back and forth. I'm sorry, Tom, you look confused?
No, there's a question here.
Oh, go ahead, please.
What potential do you use to make this evolution?
Came in a little late, so.
No, it's fine. There's no potential. What I'm doing is I'm evolving it by a mean curvature flow. So it's just we kind of discretize time, and the next time step, I say that every one of the points, I also break the boundaries into vertices, so it's kind of discretized system. I make some approximation of the curvature there, and I move every point toward the center of curvature at a rate proportional to the curvature.
So the
That's it.
assumption is that the boundary energy is proportional to length in this case?
Yes, that's right. That's right. And so it's just trying to minimize its energy. That's the only thing that's happening. But to explain that system is something completely different. That's kind of what we're working on. So we also work with a second system. This is actually a soap foam. And so for the case of a soap foam, there's the kinetics, there's two timescales associated with this. In the case of a soap foam, they're separated. So there's one timescale associated with the exchange of area between cells. There's another timescale associated with the redistribution of the area or the gas within a bubble. So for the case of grains, these two processes, the timescales overlap. In the case of a foam, they're very, very separated. And so you can idealize the system and say that the redistribution of the area within a cell happens instantaneously. So you kind of think about it, I kind of think about it as we increment time, we change the areas of the cells, we're exchanging gas between them. And then the system has as long as it wants to flow toward mechanical equilibrium, holding the gas, the area of the cells fixed. And then you update the next time step and you exchange some gas. And so it's a very different system. What this leads to is it leads to edges of constant curvature. We don't have to break these up. These are now all arcs of circles. It does other things too. One of them is we now have global systems of equations that we need to satisfy. It's no longer a local process. I was explaining before that for the case of grain growth, you can take a ball of arbitrarily small radius and determine the motion of that vertex in the next time step. You can't do that here. You actually have to solve for the configuration of the entire system in every time step. This is a typo, excuse me. We think that there's actually more topological events for this system. Notably, we don't think that you have disappearance of digons. There doesn't seem to be any way to create them for this system. But you do apparently have disappearance of trigons. And this, the number of configurations, or there's more than one configuration associated with the disappearance of a trigon. It seems to be stable to small perturbations in the locations of those edges. You also have apparently disappearance of tetragons, fourgons, to a point. They vanish continuously to a point, we think, under certain conditions. Similarly with fivegons, which is, I mean, that's pretty intense. I was not expecting that, but it seems to be true, that these things can vanish continuously to a point. And then, of course, you have the edge flip. So these are associated with an area going to 0. This is associated with the boundary length going to 0. So just really by imposing this constraint that we have edges of constant curvature, we get a very different family of topological events taking place.
So can I ask something? I'm still not understanding the edge flip. It
Yep.
maybe looks to me in the movie that you showed us that, should I think of this as those two corners come together
Mhm.
and they punch together and then they go along a line? So is that?
Yep.
So it still seems in some sense like continuous transformation. The edge doesn't just jump.
No. It's definitely a continuous transition in the case of grain growth, but the topology changes. And as soon as the topology changes, the number of sides of a grain changes, and so the rate of change of its area is the first derivative of that is discontinuous at that point. And that's what I meant. I'm sorry if that wasn't clear. This actually, it's no longer continuous in the case of foams.
That disappearance of a foreground, I didn't know if I even understood the pentagon. It just looked like two opposite sides were coming together. We're shrinking
This
two
one?
opposite edges are shrinking to points, right? It's not the whole thing's not shrinking to a point.
Yes. Yeah, the whole thing shrinks to a point. There's actually, so in this case, there's only one configuration that you can get after a trigon disappears, right? There's only one that you can build that satisfies the
So
angles
it
coming
shrinks to
together.
a point and then it comes out to an edge.
Yes.
Yes.
Okay.
Yeah, in this
We'll see
case,
the movie in a minute.
yeah, in this case it does. It happens, in our idealization, it happens instantaneously. And in fact, this final configuration is not unique. I can keep the same 4 points attached to the edges, and I can have a vertical edge there. And there's, like 5 configurations associated with this one? So there's some question about which one you pick. Yep.
But do we also have this in the foreground where it does collapse an edge and not some point?
It can. It can, depending on the arrangement of the edges. Yes, that occasionally happens.
Do you count it together? Do you count that also in the disappearance of the
That's a composition. If one of these edges goes to length 0, it's a composition of an edge flip with the disappearance of a trigon.
But it won't flatten out to an edge. That never happens.
So it won't. It will.
No.
I'm confused.
I may be confused about your question.
One edge.
I think he was answering a different question from the one you.
Yeah, I'm sorry about that
So-
then. Mm-hmm.
So I think they're asking, do these two things come down parallel?
I don't think so.
And that we don't see.
I don't think so.
What he's answering is, will this shrink to a
Yes.
point? And that does happen.
Yes. Yeah, I'm sorry. Sorry if that was confusing. Yep. Was there another question?
Yeah, so why in the flip of it you say the two corners are coming and separating again,
Yes.
but you could imagine it from the right to the left also?
Oh, yeah, yeah. I mean, this is a double-sided arrow. Yeah.
It seems that sort of points splitting into edges is happening a lot. Have you systematized how often and in what situations that can occur?
Points splitting into edges?
Well, and this flipping of an edge, it sort of squeezes to a point and then opens up some different way
Yep.
into an edge. There's a lot of points with some points in certain situations opening into edges. That seems interesting.
Well, those are singular points, right? If you look at the graph of our structure, it's trivalent. So if 4 of these points come together, it's a singular configuration. In a physical system, that would happen only for an instant, and it would immediately separate. So no, in fact, if you were to freeze one of the images in the movie and look for it, you would never see a vertex that has 4 edges coming into it. That's just, it's not physical. It's not physical, and it's not allowed, actually, in our system.
So you jump from before the flip to after the flip?
Because we work with this numerically. Yeah, that's exactly right. We kind of push past the singular point, and then we let it equilibrate a little bit.
Well, you see in the movie, the length of the edge goes continuously down to 0, but once it's at 0, immediately the other edge is.
The question is, how do you choose when you're at the 4 connection where you go? And you're saying that actually you do that, go to the 4 point, and you move on. All right.
Good question.
So, right, that goes to this configuration, right?
And then what?
So now there's only two possible results. There's this one, and then there's this one.
Go back to where
So
it started.
if there was a thermodynamic driving force to bring this to a point, why would it return? Which means that you assume that it's going to go to that configuration.
All right, so you choose.
It's imposed.
That'll minimize the energy, right?
Yeah.
Well, because that's a local argument. Because you could say that when you have shrunk, what happened everywhere else in your network pushes you to actually come back to your previous stage and to have an oscillation. But you decide no, that you have to switch.
No. It's a physical fact that there's no oscillation. It's not imposed by the numerics.
We are simulating physical systems. And so a lot of these questions, they become very obvious if you look at them physically. Right? That choice is very clear physically. There's some driving force to push that edge length to 0, and so it's not going to come out of that singular configuration with a finite length. There's no physical reason for that. So, yeah, it jumps all over the place because I have to solve for these equations. It's a coupled system of equations for every vertex location, every arc of a circle in the whole system simultaneously. In every step of time, I have to solve for the entire system. And there's just, you can't actually you see it jump around every time there's a topological event because there's certain configurations that are just not permitted. You can't build it satisfying all the rules that I put on this, that all the angles come together at 120 degrees, that these are arcs of circles, that we preserve areas of the cells through topological transitions. If you have those, you can't actually have it evolve continuously in space. It has to jump around. There's no other way you can cause this.
Do it again.
Do it again. Okay. Here it is again. And it's actually, you see at the beginning that there weren't a lot of that jumping. There wasn't very many topological transitions at the beginning. There's definitely a transient. There's definitely a transient associated with this and some kind of approach to a steady state behavior.
By the beginning, you meant
In the first couple seconds. Yeah, in the first half of a second. It looked like it was not doing anything. What was actually happening is there's a redistribution of gas between the cells, but that wasn't enough to actually cause any of these topological transitions. Now, it's picked up and, yeah, it's moving a lot. And you're right. When you have one of these edge lengths go to 0, it's very difficult to point to them in this case. It is a global event. There are kind of repercussions of that through the whole system. Physically, I find it very difficult to believe that. Well, I should also tell you that we look at this case where this edge becomes arbitrarily small. We kind of push it through the singular point, but physically this would actually collapse continuously, and then it would come out continuously, right? And so in that case, you can kind of say, well, the perturbation that you apply to the rest of the system in this transition, you can make arbitrarily small by letting this edge length become as small as you want. So you can effectively hold the rest of the system fixed. The force driving this edge length to 0 then becomes a quantity that's not strongly perturbed. So, I mean, if you wanted to, you could make this argument, but I don't think it's necessary.
I sort of tuned out briefly when you were saying this
Uh-huh.
is what this was. It's not the mean curvature flow. It's going by something else.
We call it foam evolution. We don't have any other term for it. It's not mean curvature flow. You update the areas and then you find the next stable configuration that's closest to the one you had before. That's all it is. It's a very strange thing. So I was.
So far as I know, no mathematician ever studied it. Gene Taylor proved that these things really are wise, but that's at a given instant. But the evolution, so far as I know, hasn't been studied in mathematical. Doesn't have a name.
But I'm going to talk about.
Basically, you're just letting the areas go by proportion.
I update the areas. I update the areas according to von Neumann's law.
Okay.
If I have to do any of the topological transitions I enumerated, I do them. And then I say, find the closest mechanically stable configuration, preserving the cell areas that you can. And my numerics do that. And they do it reasonably efficiently. But
By the way, he's solving 1,000 algebraic equations and 1,000 unknowns approximately.
more than that. It's about 12,000 for that system.
Yeah, I mean, just as a matter of numerical algebraic geometry, it's amazing you can do it, and it basically uses Newton's method.
Yeah. Yeah, it's
So
Big.
don't shrink automatically,
No, if you have more than 6 sides, you grow.
or grow automatically from the center? When you
No,
think
I don't specify how they grow. I just specify the areas. Everything else comes out of that system of algebraic equations. That's the only thing I do. So there's this conjecture in my field. It's so old it doesn't even have a name associated with it. It's just kind of assumed that this is true. And in this case, I'm talking about grains specifically, not so much about foams. So in that case, mean curvature flow applies. So the conjecture is that for almost any initial condition, say this one, where we have, this is on a torus, so the number of grains is finite. Say we start with n grains. So for almost any initial condition, if you evolve it long enough, it reaches some steady state. And even the definition of this steady state is not, it's not mathematically precise. I kind of think about it colloquially as any statistic you measure will reach some stable value. And this is not meant to be a rigorous argument, but the structures, the structure looks the same even after the number of grains. So between the time when the number of grains is 1/6 of its original value and 1/100th, you don't see large changes to the structure. It looks pretty much the same.
You scale the pictures, right?
Yes. Yeah, of course. So to give you some kind of evidence for this, this is an example of one statistic that we were measuring. You can think about plucking a cell or a bubble at random, a cell in this case, a cell at random, from the structure, and then counting the number of edges that it has, the number of sides. And so you end up with some distribution like this, which is not any distribution that we know of. Nobody actually knows what this thing is. We can calculate it to very great precision using these numerics, but that's all. So this is the steady state. What you can do is you can start looking at this as it evolves. So what I've done is, this started off with about 10 million grains, 10 million cells, and it evolves down to about 100,000 cells when you get over to the right. Ignore these numbers, those aren't important. And what you're looking at is the evolution of this distribution as a function of time, as it evolves, as the system evolves. And so what I've done is I've offset these things so you can see them. And you can see very clearly that, for example, the number of cells with 6 sides increases and then comes back. It's not a monotonic function. Similarly with the number of cells with 5 sides, it kind of overshoots and then stabilizes. So there's something complicated going on here, but this is meant to show you that we see this, that almost any distribution that we've measured reaches some kind of steady state. So the second part of this conjecture is that this happens, and that this happens for almost any initial condition, and that the steady state seems to be independent of what initial condition you choose.
So have you tried other initial conditions besides
Yes.
Voronoi?
Yeah. So for example, this one, what you do to construct this, so this is a Voronoi tessellation. What this is, you do a Poisson distributed points on the unit square, you do a Voronoi tessellation, you take the centroids of all the Voronoi polyhedra, and then you do a tessellation using those. Right? And you get this thing, which looks substantially different and actually is. The statistics of that are very different, but they both, I'm sorry, I'm having some problems with my computer, but they both evolve to structures that look the same. The statistics are the same, the steady states are the same, the distributions are the same. The approaches are different. The length of the transients are different. But where they stabilize seems to be independent of that. So there's Matt Kale actually, he had a suggestion about how to try to make this more mathematically precise. His suggestion was that we specify a radius. We specify the radius of some disk. If these structures are actually statistically indistinguishable, then for that disk, we should be able to find some region in this structure that matches some region in this structure. And matching, we haven't made that precise. I kind of think about it as some smooth invertible map. And then if they're statistically indistinguishable, you should be able to perform this operation for a disk of arbitrary radius in the kind of idealized mathematical structure where these things are infinite in extent. For any size radius disk, you would always be able to make that match. But that was just a proposal of Matt's that we can't prove. I thought it was very interesting, though.
So what is the proposal again? There is a mapping?
Yeah, so Matt's proposal,
Mapping, though.
a smooth and invertible one. But those are my words. That's not Matt's proposal.
I was just going to say, if they agree on a big disk up to some small epsilon, then maybe we'd say they're close.
And that, yeah.
So in particular, you'd like the actual same topology. If you have a certain topology up there, you should be able to find the exact same topology somewhere in the plane down below.
I think that would be a nice statement if that were true. Although you could imagine, so if you just look at the boundary complex as some compact set, you could compare a compact set in this disk to a compact set in this disk with like Gromov-Hausdorff distance, and they might be close even if the topology is different.
Yeah, that would be cool. That would be cool.
What about initial conditions that don't go to a steady state?
Yeah, there's a lot of those, actually. You can, for example, take a regular hexagonal lattice. That's stable indefinitely. That never moves. You can take initial conditions on the torus that exploit the fact that you're on a torus. You could have a single grain that wraps around the torus in one direction, right? That violates this. If you take a hexagonal network, a regular hexagonal network, and then cause some small perturbation to it, like you delete one of the boundaries there, what that does, that structure now evolves, but it evolves in such a way that the evolution is always kind of localized. It kind of spreads out from that center where you put it in, and it never seems to approach one of these states. So you can construct a lot of examples of this. My feeling, though, is that the space, the kind of state space of these things is so large and such high dimension that all of those conditions which do not converge may make a set of measure 0. I'm not sure about that, but it's, I mean, in the kind of, in the mathematical limit where this is an infinite structure in the plane, it seems like it may be possible.
So when you're comparing these regions, are you also considering just looking at the boundary?
This is something that Matt told me over lunch in 2 or 3 minutes. You know, I haven't put a great deal of thought into it, but I thought it would be interesting to put the idea out there. There's a number of ways that we look at this. This is one of the ways of which I'm particularly enamored. We take our cell complex, we put down some additional structure on top of it. We put down flags. Mike Davis does something very similar. He would put down a point in this and then cut this up into triangles. But there's a one-to-one mapping between the flags and those triangles. But we put down flags which are associated with a particular vertex and a particular edge. So this one is associated with this vertex and this edge and this cell, which is why it's close to that vertex and close to that edge and close inside that cell. So you have 6 of these around every one of these vertices. And then we put down operations that bring you from one flag to another flag. So for every flag, one of the advantages of this is every flag looks the same when you're sitting on top of it. There's always 3 operations, which will they'll either exchange your vertex, which are the purple ones, they'll exchange your edge, which are the yellow ones, or they'll exchange your cell, your face, which are the blue ones. And so you can put down this structure, and then you can, actually this forms a Coxeter group. Here's the Dinkin diagram, which I think I've drawn this correctly. So what you do is you have a relation of order 2 between S0 and S2. I'm not sure my language is correct, which just expresses the fact that you have this, these 4 operations that run around an edge. That's kind of graphically shown on this construction. You have a relation of order 3 between 1 and 2, S1 and S2, which runs you around a vertex. That just expresses the fact that this is it's a trivalent graph. And then these ones, you run around the interior of a cell, except there's nothing imposed by the group there. That actually, it depends on the local structure. And so then I make this claim that the stabilizer of any flag, so the set of group elements that returns the flag to itself, will completely characterize the topology of the system. If you have the stabilizer for a flag, you know everything about the topology. And you can prove that using a constructive argument. You take, for example, the smallest element in the stabilizer, the shortest element associated with a particular flag. It might run around the interior of a cell. You then take the next shortest. It might look something like this. It might run around here and then around the interior of this. And so by this kind of iterative argument, you just keep taking the next shortest element out of the stabilizer and putting down the flags and the operations associated with it. You can build out what the structure looked like. So you can reconstruct the whole thing, and then you can interrogate whatever you like about the topology.
No, I don't know where I saw these flags and stuff. So I think I once asked Bob, is this the Cayley tree for some group? Is that how you're trying to?
It's essentially a Cayley tree with additional operations that close up the gulfs. That's my interpretation of it, but yeah.
It's a Cayley diagram for an action of a group.
For an action of a group, yes. So the group acts on this.
The group acts transitively on these things. Okay. So that gives you
Yeah.
And what is the group that's acting?
I mean,
I think it's, if you took the universal cover of this picture, you would get the Cayley diagram of whatever this thing, which is like basically the usual picture for SL2Z.
Right.
The picture you always see of the the picture everybody always draws.
Which picture is that?
the tessellation of the hyperbolic plane by triangle. Right. The
3 regular tree.
Yeah. So you build this up, great. And so then the question becomes, well, that's wonderful. We need to start looking at the stabilizers. I'm sorry?
Just 3 regular trees.
Yeah. So I'm interested in getting these things numerically, in taking a structure and putting down some flags, and then asking, what are the elements of the stabilizer? How do I express those? So for example, we might start at some flag in here. Then one component of the stabilizer, one element of the stabilizer is just going to be this kind of path that runs around the interior of that cell. So that's fine. I'm also going to have things like this. So I can take, for example, the same path, and I can just kind of push it. I can add some additional operations to the interior, to the middle of that path, that just push it around a vertex, and that doesn't add anything new. There's no new structural information there. And I can just repeat this process. I can push it up along edges. I can push it around additional vertices. And you can kind of think about this thing as running out along these edges. All of these contain identical structural information. There's nothing new in this. So what do? Well, I think that it can be proven. I think we have the core of the proof. We haven't actually fleshed it out. I haven't fleshed it out. Maybe Bob has. That if you take only components of those generators in these canonical forms, in these two forms, then you are never going to get these kind of additional. How do I want to say this? Suppose that you take all combinations of generators. We're going to divide those up into equivalency classes, where I put a bunch of those in an equivalency class if they differ only by the operations imposed by the group structure. Now, I don't want to test every element in one of those equivalency classes. I only want to test one to see if it closes. Because if one element of that equivalency class closes, they all close. Because all I'm doing is I'm deforming it by these small operations. So which element in that equivalency class do I pick? I pick one of the shortest ones. And the shortest element in that equivalency class is not necessarily unique, but one of the shortest elements will always have this form. That's, I think, the precise way of saying it. Does that sound reasonable?
What do those powers mean?
So what this means is I take some S0, S1, S0, S1, S0, S1. I take pairs of those to the n0th power, where n0 is an integer. That takes me around a loop. And then I'm going to take an S2 operation, which jumps me across into the neighboring cell. And then I have some number of S0, S1, S0, S1, S0, S1 that runs me around here. And then I jump into a new cell. And then I can just repeat this. And there's some additional constraints on this, like there has to be an even number of S2 operations. But what you end up doing is you can reduce this. You can reduce these paths to just ordered sets of integers. All the n0, n1 to nn, these are just integers. Sorry?
Is this like a shelling order that you're going around? Because you're hopping from one.
I don't know what a shelling order is.
Well, like when you're hopping around
Mhm.
from
Flag to flag?
flag to flag. I don't know if I want to say flag to flag, from the two-dimensional face to two-dimensional face.
Mhm.
That's where I would say it.
Sure.
Are you doing it in such a way so you don't have things missing in the middle? I mean, it always looks like a sphere topologically.
So actually, that's an interesting thing. We've calculated that for both, right? We've calculated it for all paths of this type numerically. So we have the stabilizers for all paths of this type for a particular flag. That's actually not too difficult to do. That's still a very large set. There's still a tremendous number of elements in that stabilizer. If you only, and it's actually infinite, but say that we only look at elements of the stabilizer that have length, so a total number of operations under 70. Right? There's still a tremendous number of things in there. So I want to cut that down while retaining all the structural information so I can rebuild the structure. My impression is that it's sufficient to only look at these paths that enclose regions homeomorphic to a disk. So it has a well-defined inside and outside. And we have data on that too. But that is actually dependent on the local structure. You can't get that out of just manipulations with the group. Depending on the flag that you get, the ones that are not, say, self-intersecting or twisted, that it changes. But these are the ones that I'm specifically interested in. So
basically, you're just
yep, go ahead.
something in the stabilizer is just some big loop, right?
Yeah, it's a big loop. It's a big loop with an inside and an outside.
But you're just assuming that divides it.
If I find a figure 8, I throw it out. I don't save it. Yep, that's right. They're just big loops. That's what we're really interested in. And so there's a bunch of other work there that you had to do to get that out of this kind of group structure. But so what you do, one of the things that we've done is we collect the stabilizers for different flags. Say we have 100,000 cells. We're going to have 200,000 nodes, which makes over 1 million flags. We're going to have over 1 million flags. So for every one of those million flags, I collect the stabilizer. We look at statistics. What are the most frequent elements in the stabilizers for all of those flags? And it comes out in this order. This is the most frequent one, and then the next most frequent, and the next most frequent. And actually, I just told you a lie. What we collect group operations. We collect group elements, which we kind of encode by those integer powers of S0, S1 to some power. So I have some collection of operations. That can correspond to any number of different structures. What I've drawn here, these are just kind of the canonical ones. But going from a path, going from some sequence of operations that has one of these closed paths, the structure that corresponds to is not unique.
But this, like the left-hand one means, so you start out at the bottom, you go around the hexagon.
Yeah, you run around here,
then you, go
you
up
pop
those
out,
two edges,
you go,
then
and
you
then,
go around the pentagon,
and then
you
in.
go back.
Yep, that's right.
All right.
Yep, that's right. That's exactly what I mean by this. That the most frequent path you can put on this structure in such a way that it encloses it in a loop. That's exactly what I meant.
It's kind of amazing. We expected the most frequent thing would be a hexagon closing.
But not even close. Not even close. Hexagons are less than a third as frequent as this structure, which is weird. So there's a whole bunch of questions here, like why is this the most frequent, that I haven't gotten around to answering. I would love if a combinatorist was interested in this and could help us unravel that.
So what is the statement here? So I'm looking at I look at a steady state configuration.
Sure.
And I put this.
You put the structure on it. Yep. So we have flags,
Yeah.
a whole bunch of flags, like millions of these things. I collect the elements of the stabilizer for every flag in that system. Okay. I only examine elements of those stabilizers that enclose regions homeomorphic to a disk. Okay. So things that wrap around the interior of a grain multiple times or self-intersect, I throw those all away. So of the remaining ones,
Why do you do that?
because I don't think that they contain additional information about the structure. And there's a lot of them. And if you do that, so there's another reason actually. So
Well, what about going out along a long tail, coming around the loop and then back?
I mean, that's exactly what you see. That's exactly what you see.
That doesn't enclose a topological. I mean, this seems like it self-intersects or something,
No, it's essentially a ribbon. It's a ribbon graph, right? We put down a ribbon graph so you can.
Two sides.
Yeah. So that's why. So actually, it's more subtle than that, Tom. You're right. So suppose that we look at the components and the stabilizers of these flags up to length 50, right? I can collect the most frequent, the paths that appear in the largest number of stabilizers. And then we go out to length 60, and we do the same operation. The most frequent ones have changed. We go out to length 70, we repeat it. The most frequent ones have changed. But it seems that when you do that, there's no additional structural information there, right? What you're doing is you're running around the interior of the same loop a number of times. So you throw that away. You only take paths that enclose regions homeomorphic to a disk. These stay stable as you increase the maximum path length that you're interrogating. There seems to be something real about these guys.
It'd be interesting to compare these with what do you get as the most common things for other things that aren't your steady state. I mean, I think what you guys are describing here is like a new invariant maybe for certain, cell structures on the plane or something. But I mean, like I'm not sure what what other structure, but like you said, for example, had you actually computed this for the tied into the plane by hexagon?
Yep.
Or something like
Yep,
that?
we have.
And you just said it looks very different.
It's extraordinarily different.
Is the hexagon the most common thing there?
No.
It's not.
No, it's something similar to this, and there's a combinatorial reason why. It's something similar to this guy. Yeah, they're two hexagons, and they're separated by a number of edges. And that's purely combinatorial. There's more structures of this kind than there are just hexagons.
Can you tell us how similar or different this set is from the equivalent set for the Voronoi tessellation?
I haven't tested the Voronoi tessellation extensively. I can.
Does it change a lot as it settles?
No, I mean, they're basically the same ones. They're reordered, right? It's like, I think this one may be the most frequent. But yeah, there's a reordering of them, but it's not substantial. Like these, no.
So is that bad news because it says this won't help us characterize?
I think it will. I think we just don't know exactly what we're looking for in this data yet. It's such a new, I mean, I don't know of anybody who's ever looked at something like this before.
I don't know if it is substantial.
I think it is relevant that these things change order during the evolution of our structures away from a Voronoi tessellation to the steady state. I don't know why, but it definitely happens. That's not actually all that we can get out of that. So I showed you a list of the 10 most frequent elements of the stabilizers. You can also look at the least frequent elements, and you get something very different. So in order to motivate this, I'm going to look at this particular path, which is just a blue path. You can pretend we started at this base flag, and then we ran around here in this way, and we close up, and it's homeomorphic to a disk, and so everything's nice. I believe that this is true. I just sat down and thought about this for a little while today, and so I don't really have a lot of evidence for it, but it seems pretty reasonable to me. So let me explain what this is. What I'm talking about is I'm taking these numbers here, these integers. I'm taking the alternating sum over all the integers that represent that path. And you take the absolute value. Okay. So that's some quantity. What's here on the right-hand side? What's on the right-hand side, these mj's are the number of sides of the j'th polygon that is contained in your loop. So in this case, say m0 is going to be 6, because this one has 6 sides. 1, 2, 3, 4, 5, 6. This one has 8, and this one has 7. So there's going to be 3 terms here. It's going to be 0, 1, and 2. And you add 6 to that. These seem like they're the same. And clearly this is not proof, but in the specific case, just to give you a little more idea of what I'm talking about, say that you ran around here. Well, you go by 1, 2, 3 edges on the outside, so that's your 3. You go by 1 edge on the inside, and then 4 on the outside, and then 1 on the inside, 1 on the outside, 1 on the inside, 5 on the outside, and then 1 on the inside. The sum of that's 9. So in some sense, in my mind, this kind of looks like a 9 gon, that the region that encloses. And similarly, you take 6 plus, well, this contributes 0, this contributes 2, and this contributes 1. I would, this is just, it's really nice looking. I want it to be true. I can't prove it.
Is this only frequent elements or all elements?
This is all elements.
All elements.
I think that this is true for all elements. There's this interesting thing, though, that the least frequent ones are ones where this quantity deviates very strongly from 6. The most frequent ones, this quantity is very tightly clustered around 6. You get 6, 5, 7. For the least frequent ones, you get stuff in the range of like 1, 0, 12. That's kind of odd. It seems to me that this can be interpreted. I think this is Bob's idea, and so he understands the terminology better than I do. I thought about it a little bit. It seems to me that the scarcity of paths where this quantity deviates strongly from 6, that those are very infrequent, implies that the system is nearly flat in a kind of polyhedral sense. So I need to describe what I mean by that. So let's suppose that we take some structure, which is a 3 regular graph, or this is in fact just a Voronoi tessellation. These are schematics. This is not real data. Let's take the Delaunay triangulation. So I pick some point on the interior of these cells. It might be, this is in fact not really that great, but yeah, suppose I take the dual graph. Suppose I take the dual graph. And then what I do is I try to force every one of these triangles in the dual graph to be equilateral triangles. So you can't do that while staying in the plane. So what we do is we let it buckle out into the 3rd dimension. So suppose you let it buckle out into the 3rd dimension. what happens is you now have a height function. And the height function has positive Gaussian curvature where you have cells that are dying, where you have cells that are shrinking. It has negative Gaussian curvature where you have cells that are growing. So that's all very straightforward. How does this relate to what I was mumbling about in the previous slide? If it's polyhedrally flat, then what that means is that this surface is not going to have strong variations in its Gauss curvature. That if you look at regions and you integrate the Gauss curvature over that region, as your region size increases, the integral of the Gauss curvature over that should go to 0 fairly quickly. So can we actually see this structure? Can we see this height function? I mean, this is a real question because I think in general you can't do it. If I specify the Gauss curvature of some surface and ask you on some height function, if I specify the Gauss curvature of some height function and then tell me what the function is, I think in general you can't solve that. In general, it's not known. It's known for some specific cases. I'm wondering if it is in this case. I mean, because we know that, well, we know various things about this function. We're also, I would be very happy with even a numerical approximation to it. We don't have to have it analytically. Sorry?
What are your colors?
Roughly, they correspond to height. But this is, this is just data. I just generated some random stuff and then took some averaging to make it smooth and then put it up here. But yeah, I kind of think about this as height. Red corresponding to peaks and blue corresponding to valleys. But this is not at all related to the structure. It's just something very different.
In general, for triangulation like that,
Uh-huh.
is there a solution by making it not planar that would give you equilateral triangles?
Beats me?
What is this then?
This is kind of a proposal. This is a thought experiment. This is just some data. This is some random data actually that I applied some smoothing operators to in order to make a graphic. This is not anything real.
Oh.
This is not
It
anything.
doesn't even correspond to the
No.
height function.
I'm talking to you about an idea that we had that we haven't implemented yet. I would like some help working on it because it seems complicated. I'm not sure it could be done. But yeah, these are just some graphics to, help me with my talking points. So one of the things that would be really nice about this is if we could get this height function, then it raises the possibility in my mind that we could replace this structure, which has this kind of smooth flow punctuated by topological events, by just applying some smoothing operator to this height function, which would be really nice. I mean, that would make our lives so much easier because then you have just this continuous evolution at every point in the system. You can begin to approach that mathematically, I think. It's not, we haven't done this yet, but that's my feeling, that this would be a really interesting thing to look at. So that's my hour. I have some more that I can talk about relating to the state space of foams, but maybe that's enough for today. What do you think? Should I continue? Matt, you're the master of ceremonies. I can continue talking until you're ready to leave. Don't feel that you need to stay. How about that?
Well, maybe we could have a few more minutes.
A few more minutes?
And then continue
Okay.
the talk over to you.
Okay, yeah, because I have a bunch more pictures. Some actually, I think, really nice ones. So let's try to construct a state space of these guys. In this case, I'm working with foams, no longer with grains. So in the case of foams, this is actually a relatively straightforward thing to do. Relatively. Let's count the degrees of freedom in our system. So let's say that we have n cells in our foam on the torus. You can show without too much difficulty that the number of vertices that you have in that system is 2n. So we imagine, well, there's 2 degrees of freedom associated with the x and the y coordinates of every vertex. So we end up with 4n degrees of freedom associated with that. So now what we've done is we've put down the location of all the vertices in our system. And I told you that for a foam, all the edges are going to be arcs of circles. So for every edge in our system, we have 1 additional degree of freedom associated with where the center of that circle is. Okay? So there's 3n edges in a foam containing n cells. So we end up with 7n degrees of freedom. Okay? How many constraints do we have? Well, suppose that we have a vertex. We have 3 edges coming into it. This is actually unphysical. The reason that this is unphysical is because there's a torque associated with this, which would cause this whole system, I could just pluck it and rotate it, and all these boundaries would become straight. But another way of expressing that is the sum of the curvatures of the three boundaries around a vertex taking the appropriate signs must be 0. And in this case, they wouldn't be. So we have one constraint associated with the curvatures around every one of the 2n vertices. There is a number of additional constraints relating to the angles. I told you before that these have to be 2 pi over 3. We specify 2 of the angles for the 3 around a vertex. The third one gets specified. So that's another 2 constraints for the 2n vertices in the system. So we end up with 6n constraints, 7n degrees of freedom. There's additional complications for the torus, which I need to admit I don't completely understand. But what you end up with is you end up with n minus 1. All right, so we can talk about the state space as an n minus 1 simplex. Now, you'll have noticed that I've done something else I didn't tell you about. I already specified the topology of the system. I already specified which vertices are connected to which vertices. I had to do that at this earlier stage. So actually what we end up with is we end up with an n minus 1 simplex, where n is the number of cells in the system, crossed with all possible topologies. So for every possible topology, we end up with one of these simplices. So that's kind of cool. Let's look at this for a small number of cells. So for a small number of cells, this simplex is going to be low enough dimension we can actually visualize it. So let's take just 3 cells on the torus. I think there's only 9. I haven't proved this. But not only do I think that there's 9, we actually only see 8, which is kind of curious. There's one additional one here that I haven't drawn that we just never see. So what I'm doing in this case, I take, say, 100,000 or some large number of initial configurations, which consist of, say, 100 bubbles. And we just apply this kind of foam evolution to it until we get down to 3 bubbles. And then we say, well, which topology do you have? Right? So we see these 8. The last one we never see. OK, well, these are kind of interesting. This one is, in fact, indefinitely stable. It's got 3 6-sided grains. So it does appear that it's possible to flow into one of these stable configurations, but it happens very infrequently. And then you've got a bunch of these kind of interesting things. This one has an 11-sided grain and a 4-sided grain and a 3-sided grain. I think this one's got like 8-sided, 6-sided, and 4-sided. So it seems to me that, again, this is something I haven't proved. It seems to me that the topology for 3 grains on the torus, to specify that uniquely, it's sufficient to give just the triplet of the number of sides. But I may have gotten myself into trouble by saying that, so I'm not going to push the point.
Making a torus, but sort of Pac-Man style, identifying left and right. Okay.
Yep, that's right. That's right.
Okay, well, the upper left doesn't look quite convincing. What are the 3 cells?
Well, there's one here.
Yeah.
There's one here. And then there's one here. And I didn't draw in all the edges. It's a numerical problem. This edge should be continued here.
Oh, okay.
So yeah, there's a slight numerical issue that I was trying to gloss over. Yeah, so I apologize for that. So here's some pictures, right? So I told you that what I did is I took like a large number, 10,000 of these structures containing 100 cells, 100 bubbles each. This is actually just for, I think, 1,000. We took 1,000 structures initially containing 100 bubbles each. We evolved them down to 3 cells. Once they're down to 3 cells, we can start plotting them on one of these guys. So this is a 2 simplex. What I've done is I've labeled this with elements of the adjacency matrix. The way I interpret this, I interpret it as areas. So if we have n cells on the torus, there's n minus 1 areas that we can specify. So each one of these vertices is associated with one of these 3 cells. If your point falls here, then all of your area is concentrated in one of the cells. And as you move away from that vertex, the amount of area associated with that cell decreases. So what you see here, you have these topologies that correspond to 3 6-sided grains. We see that happen a bunch of times, but all of those points fall right in the middle of this space. So the areas need to be roughly equally distributed between those 3 cells in order for this to happen. And in fact, we can not only do this for bubbles, for foams, we can also do it for grain structures. So technically, this is not an appropriate state space for microstructures, for grain growth structures, but you can just take the triplet of areas and you can put them on a space, and you see that they fall in roughly the same spots, which is kind of curious. Let's do it for another system. So in this case, we're looking at, what is this? This is an 8-sided cell, a 5-sided cell, and a 5-sided cell. So this is the vertex corresponding to the 8-sided cell, and then the 2 5s. So what you're looking at, you kind of, I think about it as the cell, the system falls in from some higher dimensional space where it had 4 cells. So it starts here, now with 3. It evolves along this blue line, and then it terminates. So it terminates when the topology transitions. Either it goes to a new topology of 3 cells or when it goes down to 2 cells. And you see, well, I mean, there's a number of different things that can occur. All these red points correspond to one new system where you have a 10-sided cell and 2 4-sided cells. And then there's some additional things that happen out here on these edges, which are kind of nice. But and it's a very nice looking curve. And you do the same thing again with grains, and it's a lot uglier. And that makes sense because it's not a tightly constrained system. We're not constraining all the edges to be arcs of circles. There's more degrees of freedom here. So it's kind of remarkable that it looks so similar. That's really striking to me. This locus of points is almost the same as in that case. And there's other examples where this happens also. So this is an 8-sided cell, a 6, and a 4. And what you're seeing is that there's something complicated that's happening in higher dimensions, which means that when you fall into this topology, you have a very high frequency of falling in with some triplet of areas that corresponds to this region. And then you flow along your line, and then you die. And so there's a number of, there's actually...
And the lines are all parallel now because
yes,
the hexagon doesn't change in area.
Exactly. And the 8gon always changes at the same rate, and the 4gon always changes at the same rate. The rate of change of the areas is specified only by the number of sides, which is why they all have to be straight. Yes, that's right. So in this case, this is the one corresponding to the 8 and the 6 and the 4. So you're always flowing in this direction. So the 6 never changes, the 4 dies, and the 8 grows. So, and you do the same thing for grains, and again it looks similar. It's kind of feathery up here, but the topologies that you transition to, the density of the flow lines, it's all very similar. And so this is kind of our claim that, well, this is an approximate state space for a microstructure for the grain growth case. I'm almost done. So what is this? So I was kind of curious about this. I was kind of curious, well, we were getting, so this is for a foam. You evolve a foam and you get some scatter plot of points corresponding to different triplets of areas. This is for 3 6-sided grains, so it's stable. So I said, well, I actually want to know the boundary of this space. I want to know the boundary of where I'm forced into a new topology, where if I give it a triplet of areas, I can no longer support 3 6-sided grains. And so this is it, actually. You can have anywhere within this red region, you can have 3 6-sided grains. Outside that region, it's disallowed. You transition to a new topology. Actually,
You don't know the formula for that. Is that actually a circle?
No, it's not a circle. It's not a circle. These are 3 piecewise. I think that these are 3. This is smooth, and then there's some discontinuity here, and then this is smooth, and then similarly here. But I don't know the formula for that. That's one of the things we would love to figure out. Don't know. Here is the case. This is for an 8-sided cell and 2 5-sided cells. These are the same flow lines I was showing you before. You actually get something that looks, I think it's really pretty. You start somewhere in this region. And in this case, you're flowing vertically. And so you see there's this bound here, which corresponds to these red points. There's also some boundaries here where you transition to this purple one, which is an 8-sided, a 6-sided, and a 4-sided cell, which kind of run like this. They're just on the inside of the edge. And you can see those points here. They're in green. I'm sorry if they're too small. But you see a whole bunch of other things, too. That this curve looks like it just continues right down all the way to here. And similarly with this, there's this kind of lower boundary the 8-sided cell can only shrink to this point before you transition to a new topology. And that looks like it continues outside of this region too. It looks like there's all of these curves that are just intersecting, that are bounding these different regions. And it seems to me very reasonable to conjecture that those curves correspond to a particular edge in the system vanishing, going to length 0. It's, you know, I don't know how to describe them though, beyond what I've just told you. This is for an 8-sided cell, a 6-sided cell, and a 4-sided cell. So the same thing happens. You're on here and you just kind of run off, and then you transition to a new topology. You see that here also. You start off in the red and you run, you just follow along it until you hit one of these green points, and then the topology changes. So
And those purple points are only those 5 points in the low.
I think those may be real. You have to understand this is done with a finite resolution. If I had done this with a much finer mesh of points, we might have seen more detail, or we might be able to get the boundaries of this better. It's also possible that's a numerical artifact. I don't know. But even how to begin describing these curves, the boundaries to those regions, not sure how to do. It's really neat, not sure where to go with it. So that's about all I have. Any questions?